Hello, my name is Nelly Cheboi and I'm here today to talk about Diffusion Monte Carlo. Diffusion Monte Carlo is one of the variations of Monte Carlo processes, a class of numerical techniques that uses stochastic calculus to solve mathematical problems that are either too difficult or impossible to solve analytically. Although the specifics of Monte Carlo processes vary from application to application, the basic structure of such a process is as follows. A simulation involving a large iteration of an algorithm manipulates a set of data in a random fashion. From this data, an estimation of property R is made, and as the number of iterations approaches infinity, the simulated results converge to the actual empirical value of R. While the method may sound appealing at first encounter, there are details of the method are less obvious and its mathematical implementation challenging. However, once one gets the algorithm right, the simulation is a trivial task with the presence of highly efficient computers of the 21st century. Diffusion Monte Carlo is one of the numerical methods used in solving the Schrodinger equation. Equation 1. The Schrodinger equation is an eigenvalue problem with an eigenfunction psi and an eigenvalue E. The limitation of solving this problem lies in the algebraic idea of having two sets of unknown and only one equation. Consequently, the Schrodinger equation can only be solved analytically for very few highly idealized systems. Alternatively, numerical methods have been sought for more realistic systems, each one varying in accuracy, implementation, and efficiency. The most attractive quality of the DMC method is its polynomial scaling with system size, in contrast to traditional numerical methods that require exponentially more points to maintain accuracy with growth in system size. Currently, Diffusion Monte Carlo has been limited to describing just the ground state of many quantum systems, with ongoing research on excited states. After giving a little background on the Schrodinger equation, this presentation goes further to explore the formulation and implementation of the Diffusion Monte Carlo method in solving the time-dependent Schrodinger equation. The Schrodinger equation, equation 1, is a second-order partial differential equation very essential to quantum mechanics as it provides an accepted description for microscopic phenomena at non-relativistic energies. The Hamiltonian operator H has both the kinetic term, first on the right, and the potential term V. E is the energy and psi is the wave function. The wave function psi determines everything that can be known about the system. The wave function represents the probability amplitude for finding a particle at a given point in space at a given time. The actual probability of finding the particle is given by the product of the wave function with its complex conjugate. To sufficiently guarantee a non-ambiguous value of the probability, the wave function is assumed to be single-valued. The wave function may also be complex. Therefore, associating the product of the wave function with its complex conjugate ensures that the probability is a real value. Further constraints are issued on the wave function to ensure it's a valid probability function. These constraints include requiring the wave function to be normalizable, finite, and continuous function of x. These constraints are applied to the boundary condition on the solution and in the process help determine the energy eigenvalues. Real systems exhibit dependence on time. The time-independent Schrodinger equation, equation 1, will therefore not sufficiently describe them. We now look at the time-dependent Schrodinger equation, equation 3. The time-dependent Schrodinger equation is a second-order, complex partial differential equation that can be solved as follows. Separating the variables, psi on one side and the Hamiltonian on the other side, integrating on the limits of 0 to t, we get the resultant equation 6. Exponentiating equation 6, we get the two-dimensional wave function with the variable x, the position, and t, the time. The resultant two-dimensional wave function has the Hamiltonian operator on the exponent, making the task of obtaining a wave function at a later time non-trivial. We now seek at an alternative way of solving the time-dependent Schrodinger equation. Alternatively, the two-dimensional wave function resulting from the time-dependent wave function can be written as a linear superposition of the time-independent Schrodinger equation. Equation 8. Equation 8 and equation 1 from previous slides are exactly the same. The only difference is the notation. In equation 8, we have phi to represent the wave function. In equation 1, we had psi to represent the wave function. The reason for this switch is to avoid confusion because in equation 9 and 7, we have uppercase psi to represent the time-dependent wave function. Rather than having lowercase psi represent the time-independent wave function, we just switch to psi to phi. N represents the state of the system, N naught represent the ground state, N1 represent the first excited states, and so on. And X in equation 8 just represent the dimensionality of the system. So equation 8 is one-dimensional with the only variable X, which is the position. Equation 9 is two-dimensional with the variable X, the position, and T, the time. Moving on. Equation 7 is written as a linear superposition of the time-independent Schrodinger equation. So in equation 9, we see that the wave function is time-independent, phi of n, and the exponent, the e function in the exponent, is different. In equation 7, we have h in the exponent. In equation 9, we have en in the exponent. We can do this because equation 8, as mentioned before, is an eigenvalue problem, which means that taking the wave function phi, operating on it with the Hamiltonian, is exactly the same as taking the wave function and multiplying with the constant E, which is the energy. Therefore, replacing h with En just gives the exact same equation. This equation 9 is a summation, linear superposition of all the states. So from the ground state to the infinity state. In reality, and in this case, we only care about the ground state energy. As we mentioned earlier, diffusion Monte Carlo only does the ground state energy of the system. But we're adding the summation to show that the two-dimensional wave function can actually be written as a linear superposition of the one-dimensional Schrodinger equation with a phase factor of e raised to IENT over h bar. Cn represents the overlap between the time-independent wave function and the ground state of the time-dependent wave function. This property is very essential in diffusion Monte Carlo because diffusion Monte Carlo involves picking a trial wave function. In this case, it will be phi naught, and hoping that the trial wave function is big enough such that it overlaps with the real wave function, the actual wave function. Another property of Cn is that Cn is a Kronecker delta function, which has this property. On the limit from negative infinity to infinity, the overlap of two integrals is 0 when the two integrals are not the same, and 1 when the integrals are the same. This simplifies the problem a whole lot, as you'll see in the following slides. Moving on to the implementation and the formulation of diffusion Monte Carlo method, we perform two crucial transformations. One is the shift in energy scale. So the time-independent Schrodinger equation, equation 12, the Vx is replaced with Vx minus Er. Solving equation 12, integrating it, writing it as a linear superposition of the time-independent equation, using the eigenfunction and all that, we get a result of equation 13, which is that equation 13 has the En in equation 7 replaced with En minus Er. The second transformation is the Wick rotation of time. In this step, the time-dependent Schrodinger equation is transformed from a complex function to a real function. This is done by replacing t with I tau. This is crucial because in diffusion Monte Carlo, one actually treats the wave function as a probability function rather than the product of the wave function with its complex conjugate by the fundamental of quantum mechanics. Doing so requires that the wave function be real and therefore the corresponding equation also to be real. In diffusion Monte Carlo, one actually considers the solution of the Schrodinger equation in imaginary time, tau. Following the evolution of the wave function in imaginary time, one can determine both the ground state energy E0 and the corresponding ground state wave function. To see this, consider the following. Excited states have higher energy than ground state. What this means is that E0, the ground state, has a lower energy than the first excited state, E1, which has a lower or same energy as the second excited state, and so on. From this order, one can infer the following asymptotic behavior as tau goes to infinity. In a case where En is less than Er, the difference in the exponent is negative. The exponent in the exponential, therefore, is positive, and as tau goes to infinity, the wave function diverges exponentially fast. In the second case, when En is greater than Er, the difference in the exponent is positive. The exponent in the exponential is negative, and as tau goes to infinity, the wave function vanishes exponentially fast. The only time that the wave function stabilizes is when En equals to Er. So when En equals to Er, the exponent in the exponential is 0. The exponential is therefore 1, and we are left with Cn phi n. Because you're only considering the ground state, in this case, it would have converged to the overlap times the trial wave function. Moving on to the formulation of the diffusion Monte Carlo. Diffusion Monte Carlo can be formulated in two ways. The first one is based on the similarity between the time-dependent Schrodinger equation and the general diffusion equation. The second formulation arises from expressing the wave function by means of path integrals as a multidimensional integral which can be evaluated using the Monte Carlo method. Looking at the first formulation, this is the diffusion equation. This is the time-dependent Schrodinger equation. Performing the rotation of time, we have equation 18, which is basically the diffusion equation with a rate constant minus h bar over 2m. So in this formulation, the time-dependent Schrodinger equation is solved by simulating random walks of particles which are subject to birth and death processes imposed by the source and sink term. So the source and sink term in this case would be the potential energy in the Schrodinger equation. To better understand this, consider the following analogy. A group of drunk students are trying to find their way home. They can only remember so much given their impaired cognitive ability. They therefore take a random walk in the hope that somehow they'll arrive home. After some time, they lose memory of where they have been and may or may not end up exploring the same area over and over again. If one were to plot the distribution of the walks, the places they have been, the best function that fits the graph will be the wave function. The resulting eigenvalue from the Hamiltonian operating on the obtained wave function will be the energy of the system. Let's suppose that the environment is somewhat biased, that instead of an open field, there are some clues on where the direction home might be. It might be a bus or a large neon sign that says home this way. It's more likely that they would walk towards those indicators and in turn have a distribution a bit different from the earlier scenario with no clues. These indicators serve the purpose of the potential energy in the Schrodinger equation. Since potential energy vary from systems to systems, the resultant wave function also varies. The kinetic term in the Hamiltonian is the same for all systems. This formulation of the diffusion Monte Carlo requires basic knowledge of stochastic calculus. The second formulation of the DMC method, path integral formalism, arises from expressing the wave function by means of path integrals as a multi-dimensional integral which can be evaluated using the Monte Carlo method. By using path integrals, the solution of the time-dependent Schrodinger equation can be reduced in quadrature provided the initial wave function is given. Standard Monte Carlo methods allow one to evaluate numerically the path integral to any desired accuracy, provided the wave function is positive definite. In this case, as mentioned before, the wave function is interpreted as a probability density rather than the square of the absolute value of the wave function by general principle of quantum mechanics. Path integral formalism seeks a practical way to integrate the time-dependent Schrodinger equation for an arbitrary value of ER and the corresponding wave function. The solution of the time-dependent Schrodinger equation is rewritten as equation 19 in this formulation, where K, referred as a propagator, is expressed in terms of a well-known Feynman path integral modified by the replacement of T with I tau. At first glance, K looks very overwhelming, but taking a closer look at breaking the exponential part into two. The first part of the sum is the kinetic term, and the second part of the sum is the potential term. Rewriting equation 19. Equation 21 is equation 19 rewritten. In equation 21, K has been reduced by defining two functions, W and P. P relates the kinetic energy term, and it is the probability density function for a random variable xn with the mean equals to xn minus 1 and a variance equals to the square root of h bar, which is Planck's constant over 2 pi, times d tau divided by m. So the subscript xn and xn minus 1 relates in the following. Xn minus 1 is the previous step, and we get xn by taking the previous step and adding to the probability times the variance. So this represents the movement of walkers in a given time step. Wx is referred as the weight function and depends on the potential term and the reference energy. Unlike P, W is not considered a probability function. The path integral can be solved analytically only for a few particular forms of the potential function. But by choosing n sufficiently large, this integral can be evaluated to decide accurately using the Monte Carlo method. According to this method, a convergent n-dimensional integral of the form I in equation 33 can be reduced and approximated by I in equation 24. The first part of I is the normalization constant, which is gotten by getting the products of dxj from j equals 0 to big N minus 1. Big N is the total number of iterations taken. Rho is a probability function and is gotten by the product of all the probabilities from n equals 1 to big N. Rho, being a probability function, is therefore positive, and multiplying rho by the normalization factor equals 1. Replacing that chunk of equation 26 with 1 in I, we got equation 27, which is just the integral of from negative infinity to infinity of f. F is the product of all the weight functions from n equals 0 to big N multiplied by the ground state wave function. Equation 27 is therefore approximated in equation 29. The summation of f divided by 1 over n. So how does this work? Next slide. To sample this, we start at a position where the wave function is assumed to be large, process 0. We populate that position with walkers. We move each walker by probability defined by p from x0 to x1. We weight that probability by multiplying it with the weight function. Getting to x1, we move the walkers again to x2, multiply that probability by the weight function. The probability is weighted because the probability is affected by the potential energy, which is found in the weight term. We keep doing so until we get to xn. This approach is inefficient because the amount of computational effort is spent on propagating the walkers with small f. The walkers with small f means that they're in position where the potential is too small or even forbidden region, like the system cannot be there. And the ones with large f means that they are in the right, they are not in the forbidden region, and therefore have an actual representation of the system. A better approximation is to punish the walkers that are in the wrong forbidden region and to reward the walkers that are in the right region. How is this done? The first part is the same. The walkers are sampled at a position where the wave function is assumed to be large. In this case, the wave function is defined as a delta function, but it could be any function depending on the system. The next step is performing the random walk as defined by the probability, which is xn equals to xn minus 1 plus the variance times the normal random variable. Instead of multiplying the probability by the weight function, the fate of each walker is evaluated. This is done first by looking at the value of the weight function. So we take an integer value of the weight function plus u. U is a uniform random value from an interval of 0 to 1. We take the minimum of u. We take the minimum of the sum of the weight function plus u and 3. If mn equals 0, the walker is deleted, which means that the walker is at a forbidden region. If n equals 1, means that the walker is fair and is left unaffected. But if m equals to 2 or 3, the walker continues with the process and it gives birth to new walkers. So if n equals 2, it gives birth to 1 walker. If n equals 3, it gives birth to 3 walker. This is the reward because it means that when mn equals 2 or 3, it means that the walker is in the right position. It's representing the potential really well, and we want to reward that by having more walkers starting at that position. The birth rate property is important to avoid numerical instabilities. And at each step, we readjust the trial energy by taking the previous trial energy, taking the difference of 1 minus the new number of walkers, because now the number of walkers are changing because others are dying, others are giving birth, so the number of walkers are changing. So we do so by taking the current number of walkers divided by the initial number of walkers, and then we take 1 minus that. And we multiply that by h bar, which is again is Planck's constant over 2 pi over d tau. So this process is repeated over and over again until a convergence is seen. So the convergence will be that the ER has converged to a stable value. And the corresponding distribution of the walkers at that time will be the wave function. So how is this implemented? So you take the input, you initialize the walkers as defined by the wave function. You perform the walk as defined by the probability function. In the branch position, that's where you determine if the walker is going to be killed, replicated, or unaffected. You increase the count, which is increase n, and then you test. So as long as n is less than big N, you keep doing it. You also check if the ground state energy, the trial energy, has converged. And if it has converged, this means that the previous and the current there isn't so much difference between the previous ER and the current ER. If it has converged, means that the system has converged, and therefore the corresponding wave function is the true wave function. Here's an example of a system that was solved using the diffusion Monte Carlo method, the harmonic oscillator. The harmonic oscillator potential is a half times mass times omega squared times x squared. The harmonic oscillator wave function is the fourth root of pi multiplied by e to the negative x squared over 2, and the energy is h bar times omega. The picture on the right shows that the inside shows the histogramming of the walkers, the distribution of the walkers at the convergence, and it looks almost exactly as the harmonic oscillator wave function. The energy is converging to 0.5, which, assuming unit length means that h bar is equals to 1. So this means that the system was set with omega equals to 0.5. The reference energy is also converging to 0.5. So in the harmonic oscillator, using the diffusion Monte Carlo method, the result agrees exactly with the analytical results. Other systems can be solved using the diffusion Monte Carlo method. Thank you for listening to my presentation. Here are my sources. Bye.